Looks like we had some people step out.
Don't forget to turn the projector on.
Before I turn, so let's start up again. Here's what I plan to do. Let's go over some unresolved questions and a few extra details about radiation detection of nuclear materials. And let's try to take that no later than, say, 7:20. And then at 7:20, and that you can use that time to break into your semester project groups, continue to work. And I got a chance to talk with a couple of groups last time. I'd like to go around, and if there's enough folks here, talk with the other two groups. And just to reiterate, we have tonight's class and that extra time to work with the group on your group projects. Next week is 2 guest lectures.
Right. We have Bruce Goodwin and Dean Wilkin from Arsenal to speak on new trends in nuclear weapons and missile defense.
So the 18th is pretty full of 2 guest lectures. 25th is the crisis management exercise.
I'll tell you about that next week. I'll set something out during.
Then the 2nd is no class. And then the 9th is the presentation of the semester projects. So not a lot of time left. This is the last, my last lecture and the last opportunity in class to meet as a group. So I want to give you time to take advantage of that. So let me pick up, let me do a quick review. It was probably 4 sessions ago, we were talking about radiation detection as a very narrow but important topic in the idea of homeland security, preventing the transit of illicit materials, and in radiation safeguards and security. I understand it's a very narrow topic. I want to dive a little bit deeper into that for the next 20 minutes. We talked about radiation interactions, heavy ionized particles, alpha particles, very short stopping distances, not enough range to even penetrate skin. That idea, we talked about beta particles, which are essentially electrons that are emitted from nuclei. Also relatively short range. We talked about neutrons, we talked about gamma rays. As part of that discussion, when we talked about basic methods of detection, right? But the bottom line was, in almost all of them, you have to convert your ionizing radiation into ions, into charge pairs that you can collect and then measure the current, whether you do that directly in a semiconductor type detector or indirectly by getting the ionizing radiation to give off flashes of light and then collecting the light and turning the light into the current. That's still the bottom line idea. And then I don't know if you remember, I sort of, it was a little off the cuff, asked the question. I said, here's an informal homework problem. Because we were talking about sources of radiation. And we were talking about the gamma radiation from special nuclear material. And I brought up a gamma ray spectrum of uranium. And we discussed some of its features. And I asked you, where does the 1001 keV line come from? Right? It's an interesting example of how things are in the radiation. By the way, right, I should define it. When we talk about spectrum, is that clear to everybody? The idea of measuring the gamma ray energy spectrum from the source? Yeah. Okay. Because I know it may not be promoted to everybody, but of course it's basically a histogram, and we're going to keep a count. We're going to keep count of the number of incident photons that are measured, or gamma rays that are measured, measure their energy, and these are simply energy bins, bin 1, 2, 3. These can be of some delta E. And as you count them, you accrue counts in each channel, and and pretty soon you build a spectrum up over time, measuring the number of counts in a given channel. And of course, the resolution then is how fine is your delta E in any given channel, right? The finer the resolution, we talked about this as all review, the finer the resolution, the more you can distinguish characteristic or signature gamma rays from different materials. We talked about the concept of resolution, sort of the full width at half mass, full width at half width at full height. All right, myself. Pulse comes in, and depending on the material you're measuring it with, the electronics, measure the resolution, the full width at half max. I just said it right. Where this is your pulse height, and the narrower that could be, this is delta E. So, with all that in mind, did anybody go and look? Where does the 1001 keV line come from in the uranium gamma ray spectrum? Why is that there? Why is it significant? Well, here's let's just go to the answer. If you look at uranium-235, if you pick up one of the small handbooks on gamma ray signatures or look it up on the internet, there's no 1001 keV gamma ray emitted from the primary decay mechanisms for uranium-235. So it's not coming from uranium. There are primary gamma rays from uranium-235. It's not coming from the 235. If you can bring it up online, look up the gamma rays from U-238. Let's assume our material is composed entirely of 235 and 238 uranium. What are the gamma rays emitted directly from the decay of U-238, the primary decay mechanism? There are none. There are no strong gamma rays from the 238. Let me turn the okay, there we go. How's that?
Might take a minute.
Okay. Should have done it before. I'm going to bring up a chart. There you go. How do I get this to project full screen? Great. Okay. This is a chart by a colleague of mine, a colleague of George's named Tom Gosnell. Shows the decay chain for uranium-238. And it's really, there are many ways of representing it. The physical decay chain, this is a really useful one. You see in the top right corner is what he calls the primordial U-238. That exists. That's one of the pre-existing radioisotopes on Earth. It exists. It has a very long half-life, so it's still found in nature today. So there's no primary gamma rays from the U-238. What are we measuring? We're measuring the decay of the progeny. Any heavy isotope is going to decay through a series of daughter decays. And the point here, cut to the chase, really, is in many cases, nature doesn't give you primary gamma rays from the thing you're exactly looking for that you can use as your signature. 235, uranium-235 does have primary gamma rays. In uranium-238, some of the strongest gamma rays come from the progeny. In this case, I don't know, you can't see my mouse. One of the strongest gamma rays comes from the metastable state of protactinium-234. And it's an incredibly short half-life. Right? This is a daughter that decays nearly as soon as it's made. It's got a 1 minute half-life. The point is, uranium's been around so long that primarily, most of it decays through alpha decay down to thorium-234. That thorium in a cosmic sense, almost instantaneously decays to protactinium, which instantaneously, I'm saying days, minutes, it's nothing. I mean, compared to 10 to the 9th years that the uranium around nearly instantaneously decays and it starts its chain, goes to 234. The point is, you look at a gamma ray spectrum from nuclear materials, and there's an abundance of lines. And it's a skill to be able to look at the spectra and pull out and analyze the lines of interest. Let me show you an example. Oh, by the way, so this chain, of course, ends with lead being a stable isotope at the very end of this long chain. Let me go back up. Remember the curve of binding energy, right? And it seemed like everything in the universe was tending toward these stable isotopes, right? I always think of that when I look at these decay chains. These radioactive isotopes decay until they reach more stable form. But along the way, all of these daughter isotopes are emitting gamma rays, and in many of these cases, they can reach equilibria over a large period of time. So here's also a chart from Tom Gosnell. I thought it was informative. It gives an idea of the abundance of the lines from nuclear material. So these are spectra, high resolution, so taken with high purity germanium detectors, spectra of uranium ore, and background. We can discuss the importance of understanding background. That would be its own lecture on a whole another lecture. But you can see just the ore itself, even after you've subtracted the background measurement, which is at the top, you can see the large number of lines. So again, this 1001 line, this 1001 peak, that, whoop, I better stop using that. You can see it's attributed to the protactinium-234, which basically grows in a matter of, if you give it a few half-lives, in a matter of 60 or 70 days. So if I were to chemically clean, perfectly clean a sample of uranium-238, you give me pure 238, and I do some chemistry on it, and this is possible, and you completely clean out all the non-uranium isotopes in there, start the stopwatch time 0, and I take a quick measurement, am I going to see the 1001 line? No, it's going to grow in with a certain characteristic growth rate based on the decay rate of the daughters. But the point is, yeah, you have a question?
What is the T34M?
N means it's a metastable state of an isotope. When the parent decayed, in that case it was the thorium, when it decayed, it didn't go all the way to ground state. That's why so it's got different energy of gamma rays that come off and different half-life. So you don't get direct gamma rays to tell you about the presence of U-238. Although, look at this. If you were to had to analyze this and you knew nothing, your eye might go to the places where the source, the unknown of in this case, it is known as the source, the uranium ore spectrum. Where is it significantly different than the background? And your eye might go to the 100 to 200 region. And it's interestingly enough, and Tom's document, he points out that if you take measurement of, now this is not ore. Remember, what's the percentage of the 238 in the ore? 99.3, right, percent 238. The 1001 was very strong. Now we're going to switch it to highly enriched, 93% enriched uranium. And just look at that very low energy region. There are principal U-235 peaks. That's an important distinction. These are gamma rays that are emitted directly from the decay of U-235. So that's nice. It's like a direct fingerprint. You don't have to do it indirectly. What this all comes down to is if you want to truly understand the composition of a material, whether it's natural uranium, and perfect, I guess under the categories that George was pointing out, that would be very different than highly enriched. There'd be different rules that would apply there. If you want to do a measurement that can tell you the difference between natural, low enriched, high enriched uranium, you're going to need to have very good measurements. And here's, again, from the same report, you can see this is a comparison offset to facilitate a visual analysis, but this is a comparison of the different spectra for depleted uranium. So that's where the 235 actually been reduced to below natural abundance, low enriched uranium, and the weapons grade 93% enriched uranium. And of course, you can see the relative, right, so the ratio, the relative intensity of those primary U-235 peaks are enhanced, as you would expect, for the highly enriched uranium relative to the depleted uranium.
Okay. How different are the spectra between, say, 5% and 25%? Because there's a significant difference in terms of regulation, right? But
Well, with the right measurement, that's discernible. And that's a great segment, it's a great point. If it's shielded, if it's heavily shielded, doesn't matter what your detection is, you're probably not going to see it. If it's unshielded, but you don't have very good, in this case, resolution, energy resolution, that's not going to help either. Matter of fact, that may be my next slide. No, my next slide is going to point out, we've been talking about uranium, but this is a different report from Tom. I tried to have everything referenced to Tom. This is a different report, but I want to get the same ideas across. This is an unclassified weapons-grade plutonium sphere, a spectrum from a unclassified weapons-grade plutonium sphere. And what Tom's shown you in this figure is that there are certain regions of interest, just like that, 140 to 200 region in uranium. There's certain regions of interest in plutonium that give you important ratios between primary gamma rays and the gamma rays from progeny and other materials that can give you important ratios that can help you understand the composition, the time at which material might have been processed or chemically treated, right? And how long it takes for certain other isotopes to grow in. Those ratios between peaks will change over time. So I won't go into as much detail about the plutonium, but the story is the same. Even the idea with the plutonium, this is one of those regions zoomed in. And again, you can see there's certain peaks that are directly from the plutonium-239. There's certain peaks that are from americium-241. Why is there americium-241 in plutonium? Certainly in weapons-grade plutonium. Why? How does that get in there? Yeah. What would the decay be? I mean, it's similar. It's similar to what when we were discussing breeding and converting. We talked about that, the double beta decays. Yeah, did you? Yeah, I already wrote that, but it's the same idea. You have uranium-238. So plutonium's not naturally occurring. It's coming from the irradiation of the fuel. And we talked about the idea of conversion or breeding reactors where you load in U-238 and subject it to high neutron flux. And in this case, you'll produce uranium-239 and N-gamma reacts on 239. And that 239 then can, let's see, double beta decay to plutonium-239, which is what you want. That plutonium itself can now have subsequent neutron capture, go to plutonium-241, which beta decays to the americium. The point is, all these reactions are happening to different degrees when you run the nuclear fuel through the reactor. So if you're going to produce plutonium, you're inevitably going to be producing through decay, through the beta decay, americium-241. And when you look at a plutonium's gamma ray spectrum, really many of the lines you're looking at are truly americium lines. It's considered a plutonium, it's a plutonium spectrum, but technically it's a mixture of plutonium and americium and other isotopes in there. And again, the better your data, the finer the resolution, the better you can understand its composition, how it was made, when it was made, important things that may be critical to verification and safeguards. I just include these are another way to represent decay chains in that these were on a Berkeley.edu website. And the one on the left is the U235 decay chain, which doesn't have it there, but the point we're talking about is that alpha decay in the 235 gives you primary gamma rays, whereas the alpha decay of uranium-238 does not. And you rely on the gamma rays from the progeny. So this really all boils down to how well you can measure the data. I want to give you an example that we started the discussion by talking about the importance of energy resolution. And I'd like to wrap it up with that as well. The spectrum on top, this is from the same source. The isotope is in critical, these are silver 110 radioisotope sources. The one on top is measured with the sodium iodide crystal. What's the resolution of sodium iodide roughly? 4 to, it's like 5 on the average of 5%, 5 to 8, 4 to 8, something like that. So that's again the ratio full width, half mass. And then what's the resolution of high purity germanium? Yeah, 0.25%. Order of magnitude better at least. So you can see the importance of the resolution for being able to pick out information on ratios between specific peaks. If I were to say, what's the lowest, what's a really low resolution detector material that's commonly used for gross counting? I mean, it can do very coarse spectroscopy, but generally, what are big, you go through a port, like a shipping container port or other places, what are those big panels? What are those big panels, what do those tend to be made out of? They're typically plastic. I always think of them as PVT, right? Polyvinyl, toluene or whatever, but maybe there's different formulations, but they're these big plastic scintillators. They're relatively cheap and rugged. They're not like, they don't attract moisture like sodium iodide, and they're easy to make. But you get what's the energy resolution out of there? It's pretty bad, isn't it? Like 25%. It almost obviates real detailed gamma ray spectroscopy. Lanthanum bromide is similar to sodium iodide, gets 3%, but you have to get to detectors like right now HP, the solid state detectors, basically semiconductor-based detectors get you below 1%. So those are things I wanted to get across. Yeah.
I also have further questions on the previous page. I can appreciate the need for the energy spectral resolution. But then you have these different half-lives, right? So when one is doing like a radiation detection scheme or if you're constructing your process, do you look for like the emergence of peaks on a time scale that you can apply?
Yes.
Right?
Yes.
You don't need to sample as high a resolution space, for example, in principle.
Well, yeah, you can look in certain areas. You can focus you can change like the gain on your system to look at peaks only in a certain energy range. Yes, I mean the key there is the Bateman equations, right? That which describe the ingrowth of all these daughters and their intensity over time. As a matter of fact, Tom, one of the first things I worked on at the lab was to sort of update a piece of software that Tom had written, which basically solves the Bateman equations for material. You put in the material specifications at time 0, and it goes through all the decay chains, calculates all the ingrowth of the daughter products and then their daughter products, looks up all the gamma rays that come off of all those progeny, and gives it to you in a format suitable for plugging back into a computer program to simulate radiation transport. That's exactly it. And you may determine that at certain times you're more concerned about the ratio between certain energy peaks and others don't go in or get smeared out by a continuum, right? Because as gamma rays, if you emit a 2 MeV gamma ray, by the time you detect it, it may have interacted a number of times and you may not detect the full energy.
So in terms of monitoring and verification, is speed dominant? Like, do we have a need for speed, or is it more than a need for spectral resolution? Or, I mean, I'm sure there's a trade-off, but I'm just interested.
When you say speed, you mean, I'm not tracking like,
Like, do you need to be able to take a picture of a truck going through a gate and you have 3 seconds to get it, or
so I
or
think what you're getting at is efficiency. Is that what you mean?
it's like your signal nodes, you know, right? Like, can you integrate for a huge amount of time and collect like very high resolution that is a viable monitoring verification scheme, or is a lot of the research and the design of the process emphasizing?
It's a really good question, and I think they're all trade-offs. And it depends on the application. If the goal is to detect the presence or non-presence of radioactive material, then spectroscopy, you don't need spectroscopy. And you can do gross counting, you can use larger detectors. Now, that's not always so simple, because the larger your detector, the more background you're going to detect. And like I said, that's its own discussion. You may need to take certain measures to reduce the amount of natural background. We talked about that. What are the sources of, say, natural gamma ray background? You put out a gamma ray detector, a big PVT panel somewhere, you're going to detect background radiation. Where's it? It's coming from
Cosmic rays, you get them.
cosmic rays is a source of, especially neutrons. Yeah, there's norm, right? There's the ground is norm, everything. We talk about, there's uranium everywhere. The center of the earth is hot because it's full of decaying radioisotopes. And you have, depending on the atmospheric conditions, soil can get pulled into the air. You can have certain types of concentrated norm. If somebody comes by with, people like to talk about bananas, right? But the only idea is that certain plants will concentrate certain isotopes like potassium, of which there is a naturally occurring radioactive form of potassium. And if you concentrate enough of it in a cargo container, you might see it. So yeah, but that I've got off track. If your objective is gross counting, then you need efficiency and you need to manage background. If you need to, but there's a problem there. If you're going to respond to every alarm with high-paid scientists or even busy cargo inspectors, and they're going to have to go, they're going to look at the first 10 shipments of bananas, and they're going to stop looking at some point, right? So maybe you have to go to some kind of isotope identification. And now you're in essence cutting your measurements into thin bins. You're losing statistics. So it becomes a trade-off. So they're both important. Now, I'd say, I don't know, I'd defer to George if there's really spectroscopy used at a verification safeguards level, or if it's really confirming the presence of certain materials where they're supposed to be.
These spectroscopy in some situations, they use to a greater extent collimated systems to give them duration measurements, because you got a self-shielding problem. You're looking at the ratio of the 186 line to other things, and then 186 line. If you just don't do it in a collimated manner, you have to have a really thick sample. Basically, answer your questions. Yeah, they do use spectroscopy, but they use other things. They use there's a word.
That's HPG.
Yeah, they use the detective. They use the detective now as well, which is an HPG.
I think I also was really where they're installing sodium iodide detectors on a bunch of the sites with the centrifuges. So that's really gross. Yeah, just like these theoretical articles where they're just producing all these small sodium iodides and track enrichment from all these centrifuges.
Mike, I thought you were going to get a question about the advanced spectral portal.
Oh. When George and I worked together in a group called the